Numeric Tensor Framework toward a new paradigm in scientific/technical computing. My name is Dr. Dileepan Joseph. I'm from the Department of Electrical and Computer Engineering at the University of Alberta in Edmonton, Canada. This is an edited version of a talk I gave to a small group at YouTube on January 27th, 2020. I'd like to thank Neil Birkbeck of Google for inviting me, that he took the picture that you see right here, and for a tour of Google's Mountain View, California campus. At that talk, I was discussing research I did with my former PhD student, Adam Harrison. I presented slides Adam made for his PhD public seminar. So this was quite a few years ago, on November 3rd, 2015. Some of that work, though, would be published later in 2018. Now, Adam's complete thesis, called Numeric Tensor Framework Toward a New Paradigm in Technical Computing, is available online from the University of Alberta's library. So why am I making this talk now? Well, I'll come to that in a second, but I want to share with you what was great about this work that I'm so proud of, that we did together, myself and Adam, whom you see in this picture here. One of the simplest ways to do that is to give you the opinion of an external examiner. So PhD theses have a team of examiners who read this, and one of them is from outside the home university of the student. So this external examiner, a professor who has a background in computational science, including quantum chemistry models from first principles, wrote, "The thesis begins with an eloquently written chapter to motivate the work using Thomas Kuhn's view on paradigms and their significance for advancing science as laid out in his treatise, The Structure of Scientific Revolutions." So Thomas Kuhn wrote the book Structure of Scientific Revolutions. Harrison makes a compelling argument that a currently dominant paradigm in technical computing, the matrix vector paradigm, is inadequate in effectively handling several anomalies. So this picture that you see here is shortly after Adam won Best Doctoral Thesis Award in our department. Now, beyond Adam's actual thesis, afterwards, we did go on to publish some of the specific work related to advances in computing. And there were some publications earlier on some applications to imaging problems, but I would want to mention that Adam's work led to a 2016 publication in the Journal of Computational Science and a 2018 publication in the Society of Industrial and Applied Mathematics Journal of Scientific Computing. Adam and I, we developed a numeric tensor framework for what at the time we called technical computing. We did intend it to also include applications in just science itself, but we wanted to emphasize industrial side of computing. But now anyway, I think it's better just to call it scientific/technical computing. So why did I come back to this work? Well, very recently, I had a paper on follow-up work inspired by this longer-term research program where Adam played a foundational role. So recently, I had a paper accepted by the Journal of Imaging Science and Technology on a Ricci notation tensor framework. So I decided to revisit my 2020 Google talk to make this presentation on that occasion. In this part of the talk, I'm going to discuss two of the four main contributions of Adam's PhD thesis. They concern synthesis and formalism. Synthesis addresses motivation for the thesis as a whole, and as well as the literature, particularly that concerning literature review, particularly concerning arguments about paradigms. We define technical computing to include all of numerical methods and intersect with applied math. Technical computing underpins much of modern scientific practice. Normally, practitioners use technical computing to answer questions they have from other disciplines. Rarely do we think about how technical computing affects what questions we ask in the first place. So then when we start to look at that, we can classify, well, these are the questions that are being asked if you look at the literature, and these are the questions that are not being asked or not being widely asked. We believe that important questions about technical computing are not widely being asked. We are questioning assumptions in a scientific discipline. This brings us to Kuhn's theory of paradigms. Thomas S. Kuhn, a famous 20th century philosopher and historian of science, gives us tools to perform such an examination. Kuhn altered understanding of science with concepts like paradigm. Paradigms define a taxonomy that categorizes selected phenomena, problems, and solutions within a discipline as exemplars. They define a discipline's normal scientific practice and anomalies, problems outside the bounds of normal practice. Paradigms are under tension when practitioners increasingly encounter significant anomalies. Progress occurs through, in part, paradigm shifts. Kuhn didn't specifically address computing in his work, so we translated, with the help of other literature, Kuhn's terminology to technical computing. Kuhn favored theory, but he also mentions instrumentation. We looked at work by Erickson et al., who focused on applied math, which intersects technical computing. And Erickson et al. Talk about the body and soul of applied math, where body is the constructivism and soul is formalism. We map this quite nicely to instrumentation and theory. So we put theory and instrumentation mapped to algebra and software. Algebra is used to formulate a solution to a problem. Software is used to construct a solution to a problem. Unlike Kuhn, but like Erickson et al., we put them on an equally important footing. They together form a framework. Now, we have a discipline, technical computing or scientific technical computing, and there could be multiple frameworks we could use within this discipline. One of which is the matrix vector framework. Well, we argue that the matrix vector framework is technical computing's paradigm. Why is that the case? It dominates technical computing's practice and history. It's a central topic of undergraduate level technical computing textbooks. It forms the core of fourth generation programming languages and environments like MATLAB, which has called itself the language of technical computing. The matrix vector framework defines exemplars for technical computing, particularly linear mappings applied to vectors. It also defines anomalies, unaddressed phenomena that are not easily addressed by the framework itself. So looking at the literature, what are some examples of anomalies? Well, we categorized what we saw into one called special linear mappings. These generalize what the matrix vector framework is very good at to higher degree. So we call these not higher dimensional, not n-dimensional linear mappings, but higher degree, n-degree linear mappings. Why? Because, well, a vector with 3 entries is a 3-dimensional vector. A vector with 4 or 5 entries is a 4-dimensional, 5-dimensional vector. And you can represent linear mappings from one such vector space to another with a matrix multiplication. Rather, we want to look at differences from going from a scalar to a vector to a matrix and to, well, higher degree, right? Not higher dimensional data structures. So consider an image in its natural form and the edges in the image. So we can talk about a linear operation called a Laplacian that produces an image from an image where we can see where the edges are. This is a higher degree mapping in its natural form. What about entry-wise products? They are also another example that don't nicely fit into the matrix vector paradigm. You could use a diagonal matrix, but it's not an entry-wise vector product to do like an entry-wise vector product. But with an image, this is quite common in imaging to do an entry-wise product, for example, image masking. So here you see a source image where we are doing an entry-wise product with a mask to get separate the foreground from the background. Adam did an analysis of 30 toolboxes from release 2014 of MATLAB. And from his analysis, he identified which lines of code had arithmetic in the toolboxes. And of those, he found 3.4% had special linear mappings, such as entry-wise products. Another category of anomalies we called mappings beyond linear. These refer to multilinear and polynomial systems of equations, which when we categorize kinds of equations, systems of equations that we look at in numerical methods, there seems to be categorized in a sensible way. You can find that there appears to be a hole in the types of algorithms we have. So you see in this table, one column refers to systems of equations with one unknown variable. Another column refers to multivariate systems where there are multiple unknown variables. So typically you need as many equations as you have variables to solve a system. Now, usually we categorize systems also as linear and nonlinear, but you can see here that we've divided nonlinear into polynomial and nonlinear and non-polynomial. So these boxes identify not only the methods, the fact that we have algorithms for 5 of these 6 cases, specific to 5 of these 6 cases, we also have a consensus on how to represent or model such a system. The one that's the obvious hole is the case of multivariate polynomial systems. There are some symbolic approaches, but they struggle with approximate and numeric data. Another aspect from beyond linear is kind of related to the concept of factorizations, the tensor decomposition. So there is an aspect of matrix vector algebra called singular value decomposition, which allows you to separate a matrix into components based on vector products. So that can be generalized to higher degree data, and this is called tensor decomposition. And there are people who are interested in this, and this is one of the aspects that goes beyond linear. This example here is the data cube has information about human faces, and you'll see here that it's possible, according to this work from Vasilescu and Terzopoulos, to use a SVD-like decomposition to separate out data that primarily tells you about people versus the views in the images versus the illumination conditions. And this is not a machine learning approach. This is more like a model-based approach. So there are lots of people we've found, growing number of people, sorry, let me rephrase that. Most people take the paradigm for granted, but in the literature, we do find people questioning pushing at the boundaries. And so this, in the context of Kuhn's theory, allows us to link these different works together, and it allows us to argue that the matrix vector paradigm is under tension. So there's this, why do we call this a growing crowd of researchers? Because there's this experiment from social psychology that says, if you have one person standing on a corner looking up, people just sort of ignore that person and just pass them by. But if there's 2 people or more people, then other people stop and look up in the same direction, right? So there are actually people out there from different fields, a variety of fields, questioning the limits of scientific technical computing. And in Adam's thesis, we go on to talk about where we think this could go. So we first established there is a crisis. Technical computing is undergoing a revisionary period, using terminology from Kuhn. Well, sorry, let me rephrase that. We didn't want to use the term crisis as much because, we just wanted to establish that, we felt more comfortable calling it a revisionary period. So we put crisis in quotation marks. So there are competing articulations for algebra, for software. There's debate over fundamentals. People actually use words. This connects to Kuhn's views on really it's about science as a human endeavor, where people talk about finding the way things work in a paradigm as troublesome, cumbersome, unpleasant, awkward. Well, we found exactly those words in technical computing literature. So possible resolutions. Maybe the matrix vector paradigm resolves the crisis. That has happened in historical examples of paradigms under tension. We think this is unlikely. Another possibility, specialization forms with its own paradigm. What about a paradigm shift of the entire technical computing discipline? So we argue in Adam's thesis that whether 2 or 3 occurs depends on what anomalies are elevated to exemplars. So the special linear mappings, the tensor decomposition, those are very popular areas for those pushing at the boundaries of the paradigm. We think that will make 2 more likely. The much harder problem is to solve systems of polynomial equations in a numeric way. We think if that's possible, and that's connected to this beyond matrix vector paradigm pushes, then that will make 3 more likely. So what have we done more specifically with respect to advancing technical computing? Well, apart from this literature review I was talking about, framing in the context of Kuhn's work, we also focus on numeric tensors. We suggest that propose a numeric tensor framework, which includes a specific formalism we call numeric tensor algebra and a specific constructivism, numeric tensor software, as a way that we think can help move in the right direction. So we show that this framework, which uses sort of extensions to Einstein notation, provides a high degree data with versatile arithmetic operations, and they connect to some of the complaints, the key characteristics we observe in the growing crowd's work. And our software that goes with this algebra can naturally accommodate these numeric tensors, in a programmatic approach, computationally efficient as well. So we also, connecting to Kuhn's work, it's important to have certain exemplars. So we have also some proposed example problems drawn from our interest in imaging, computer vision, as well as image processing. And we use the numeric tensor framework we propose to advance them. Just a couple of citations that were included in this part of the talk, I've sort of listed them here, but I want to note in passing that Adam's thesis has 257 citations in total, which include 86 in the first chapter on a paradigm examined and 25 on the last chapter toward a new paradigm. So we really took a very serious approach to this question of paradigms. Let's discuss the numeric tensor algebra, the formalism proposed by Adam's thesis. After reviewing work from 44 publications in 12 different fields, we identified 5 important algebraic qualities of high-degree formalisms. So one of them was the ability to operate upon data of any degree. So n-degree support. Another, associativity. Another, commutativity. So this is something very fundamental to algebraic manipulations, the ability to move operands around, in particular when you have multiple multi-operand product. Entry-wise products. So in matrix vector algebra, inner and outer products are fundamental, but especially in applications to imaging, entry-wise products are quite useful. So can we incorporate them as a more fundamental part of the algebraic framework? Linear invertibility, the solution of high-degree equations. It was the 5th characteristic. Okay, so there are some categories we could give to names we could give to the things we find in the literature. One of them is called extended matrix vector algebra. There are 4 others here. The other one I want to highlight here is the last one, Einstein notation. So extended matrix vector algebra, the kind of thing that we naturally do with a programming language, and its implied algebra it supports, like MATLAB, blurs the boundary of the matrix vector paradigm. For example, we have that dot times multiplication, but we don't see that this can help us satisfy the first 3 criteria, that is to nicely model high degree relationships with complete associativity and commutativity. Instead, we went to what we called Einstein notation. It's an index notation with the Einstein summation convention, because this provides us complete associativity and commutativity and ability to deal with n degree data quite easily. And what we did is thinking about the kinds of things we want to apply to problems in computing, in particular like imaging problems. What kind of models would we construct? Well, we want to also model entry-wise relationships and also have inverses, linear inverses, easily defined. So the foundation of Einstein notation, right, provided us the high degree and full support for multilinear mappings. What we did is we took the matrix vector algebra. We didn't want to lose anything we already had in the paradigm, and we combined it with a portion of the index notation with Einstein summation convention to create this numeric tensor algebra with some extensions of our own. So the extensions were connecting the entry-wise products from extended matrix vector algebra into this numeric tensor algebra, right, and also providing linear inversions for tensor expressions on the same footing as matrix type inversions. We didn't take geometric tensor capabilities associated with index notations with Einstein conventions. So indices define tensors. So the number of indices tells you what the degree is. So an image could be represented with 2 indices. It becomes a 2nd degree numeric tensor. We could have a 4th degree numeric tensor. This could be a Laplacian operator. So an image represented as a degree 2 tensor is shown here on the right. And for one particular pair of values for 2 of the indices, you can look at this 4th degree Laplacian operator to calculate one particular result here in the output image. It's a linear mapping from an input image to an output image, but you only see a portion here of the Laplacian. Well, I guess the animation didn't work here, but that's okay. So what did we do? We extend Einstein notation to provide a comprehensive and universal algebra to work with high degree data. We can model entry-wise products with an underline on indices where normally Einstein notation means if you repeat an index, you get a summation. You don't have to put a summation symbol. So we want to suppress the summation, and we use the underline here to do that. And we can show there's a connection to inner products. This is elaborated on in the thesis and related publications. We can model high degree linear inversion. So we talked about, just like there are matrix inverses, what are numeric tensor inverses? And then these are connected to systems of equations, and they could be overdetermined or underdetermined, which involve pseudo inverses to solve them. So we even talked about that. We also have modeling approaches which involve partial differentiation, in particular when we want to optimize with respect to some variable. We talked about how this notation can help with those kinds of modeling purposes. And we didn't give up on the strengths of the matrix vector paradigm, because we could just put indices on vectors or matrices and use the same notational aspects we talked about with scalars to have vector and matrix numeric tensors. And then we could also talk about nonlinear functions that operate, for example, entry-wise on a tensor, even if it's a scalar with multiple indices. So the literature talks about canonical polyadic decomposition as an application beyond the matrix vector paradigm. This has been represented usually with 2 notations, as an extended matrix vector algebra, as well as what's called an n-mode notation. The EMV algebra represents the linear inversions, some of the entry-wise products well, but doesn't really represent the high degree data, as well as, for example, the alternative that has been proposed by others interested in beyond ordinary linear mappings. So this can represent high degree data, the n-mode notation, but it does not really model the linear inversion and entry-wise products so well as EMV algebra. So our NT algebra can do all of the above, and the thesis sort of shows some equations that make this more concrete.